So let's talk about properties of rational exponents. I want to say here that these properties of rational exponents are properties that you've already been exposed to. These are the properties of exponents that we've seen before. If I have a power times a power, I can add the exponents together. If I have a power of a power, if I have a power of a power, then I multiply the exponents. And if I have a power of a product, then I apply that power to all the factors in the product. Negative exponents, zero exponents, quotient of powers, a power divided by a power, as long as the base is the same, I can subtract the exponents. Power of a quotient, the exponent is applied to the numerator and to the denominator. So all of these things we've seen before, turns out they apply when we have rational or fractional exponents as well. So anyways, let's take a look and see one interesting thing that we can do with rational exponents. Let's say that we have something like a to the power of m, and we want to multiply that times, better yet, I'm sorry, we want to raise that to the power of 1 over n. We get an interesting result when we try this. See, what happens is we end up multiplying together. This is a power of a power, and so therefore we multiply the exponents together. So this will be a raised to the power of m times 1 over n. And if you recall, what we know about fractions is that if you have that, that's the same as a to the power of m divided by n. Now, as long as I have this written out here like such, I'm going to tell you a couple of interesting things. This guy down below, this will always be the root. So this guy right there will always be the index of the root. Always. And this guy up here will always be the power. Always. Now, I've heard of some people who have interesting ways to visualize this stuff. For instance, some people have taken the perspective that, if you think of how a flower is designed, you might recall that flowers, let me go ahead and give this guy a nice green stem. Flowers usually have some kind of stem, and then that stem usually leads to the ground, to the earth, right? And then this part down here, we usually call it, this guy down here, we usually call that guy the root, right? And it's down below, and so is this root. And then on top, we'll remember there's the power, just like the flowers on top, right? So this is kind of flower power, if I may, right? There's the flower, it's on top. If you'd like, you can call it the power. And then there's the root down below. Flower power on top, root down below. Okay, sorry. Let's get back in action here. So if we see a power where the exponent is a fraction, the top part's the power, the bottom part's the root. And so what happens is that means that we can rewrite something like a to the m divided by n. We can rewrite that as the nth root, n, of a to the m. We can rewrite it that way. And also, it turns out we have a choice. We actually could, if we'd like to, rewrite it in this way, with n here and a here, and just put a big old set of parentheses around all this, and then put the power of m there. See, the thing is, we can write it either way, because a to the m divided by n could be broken up like this. It could be written as m times 1 over n, but it could also be written as a to the 1 over n times m. And one way you're doing the power first and then the root, and the other way you're doing the root first and then the power, right? So these are all possibilities. Now let's try some other neat things. So we just tried power of a power to some degree. We did it with variables. Let's try product of powers. So what if we have something like 5 raised to the power of 1/2, and we multiply that times 5 raised to the power of 1/3. What's that going to look like? Well, it turns out you're going to add the two exponents together. So it's not obvious that that's what you would do. I'm going to remind you guys that, if we had something like x squared times x cubed, and you should be going back to this older stuff that we've learned, you could just write out the x's and you could see, sure enough, if we write out all the x's, we're going to get x to the fifth power. And so therefore we know 2 plus 3. Here it is not obvious, so you must know the rule. And if you don't know the rule, you can always go back to a problem that you understand, like x squared times x cubed. So anyways, this is just a power times a power. This is a power times a power. And when you have a power times a power, we call that a product of powers, because product is the result of a multiplication. And here's two powers being multiplied. All right, let's go ahead and see what happens. So 5 to the 1/2 plus 1/3. So if you guys enjoyed your time with fractions, you're going to love this. We're going to need to find a common denominator and then add. And so in this case, we have I'll multiply the top and bottom by 3, so we get 3 over 6. And I'll multiply the top and bottom by 2, so we get 2 over 6. And that leaves us with 5 to the power of 5 over 6. And if we had to rewrite that as that could be the answer all by itself. It depends on what the question's asking for. If we are merely presented with a problem that looks like this, and we're asked to simplify or to multiply, then this is the best result, because we started off with rational exponent form and we ended up with rational exponent form. Now, if for some reason we were told to get the answer in radical form, well, that's a whole nother thing. So again, this is rational exponent form, so you might want to add those words to your notes. And if we were asked to get the answer in radical form, it might look like this. We'll have 5, and we will have, remember which part is the power and which part is the root? The root is 6, so we'll put that little number right down here. And the power is 5, and we have choices about where we want to put that. We can either put the power of 5 right here inside the radical sign, make it 5 to the power of 5, and then take the 6th root. Or we have a choice. We actually could rewrite the same thing as, again, root 6, root 6 of 5, and then raise that whole thing to the power of 5. Either one of those guys is perfectly legitimate. And let me just do that just to make it so it looks a little prettier. There we go. All right. All right, let's have a little bit of fun here. So what if we take 64 and divide it by 64 to the 1/3 power? We're going to go ahead and take advantage of the quotient of powers. If we have a power divided by a power, then we subtract the exponents. The only thing that's a little tricky here is what's the exponent of this top guy? Hopefully you have realized that it's a 1. And so for that reason, we're going to do 64 to the 1 minus 1/3. That is one way to use this power in order to translate. So then we get 64 to the power of 2/3. And now again, you have to realize one of the two, either the 2 or the 3, is the root or the power. And you guys need to know which is which. I'm going to tell you right now, the 3 is the root. And if we could not take a 3rd root of 64, then we'd stop right here. But we can. It turns out that 4 times 4 times 4 is 64. So therefore, the 3rd root of 64 is 4. So we'll go ahead and rewrite this as, let me think about this. I think I'm going to do, I could write it as a radical if I'd like, or a fractional. Let's just write it as a radical for a second. This will be the cube root of 64, and then after we're done, we will then raise that to the power of 2. And if we look at things in that way, then what we'll say is cube root of 64 is 4, and it's still raised to the power of 2, and finally that gets us 16. Now it turns out it doesn't matter what path, there's other ways that we could have gone from here to there, but no matter what path we took, we should have got 16. If you try it on your calculator, you should be able to do 64, again on your calculator, maybe 64 raised to the power of, make sure in parentheses 2 divided by 3, you should be getting 16. Okay, so now we've taken a look at least at product of powers, power of a power, and quotient of powers. And that's a pretty good intro to the things that we can do with rational exponents, and a little bit of how it's related to the radicals that we love as well.